Word. All right. So if I'm not mistaken, what this is, let's see. Yeah, this is lecture number 22. No, 21. And today is the 30th. Oh yes, and about your exams, uh, I have still to a while to go in terms of grading them, but I'll grade them by probably by Wednesday. Okay, it's a lot to grade for two classes. All right, so don't worry about that for now. Okay, so we're gonna be talking about uh, optimization. So the big topic is optimization. It's the big one. But we're gonna first touch upon um, what's called absolute extrema. So that's the first big topic here. Absolute extrema. So yeah, I decided to choose a different color for the background this time and see how it goes. So is related to relative extrema. Remember we talked about relative, we talked about something that's local max and local min. But today we're going to talk about absolute max and absolute min. And what that means is we're going to be considering what's the maximum value among the whole interval. What's the minimum value among a whole specified interval? So we're looking for the maximum. It's the max, the maximum or minimum of a function throughout the whole specified interval. So normally we've been looking at the we've been trying to find the relative extrema, right? We would need to find the critical numbers, right? And then we just had to figure out whether it's a local max or a local min using either the first derivative test or using the second derivative test. Um, and we did not really care whether that minimum or maximum was the highest or was the lowest among all of the different points. We didn't really care about that. But now we are. Now we are going to care. Okay. So let's look at an example. So for example, what if I have this function here? 2x squared plus 3x minus 4. No, pardon me. I meant to say x squared minus 2x minus 3. And my interval is -2 comma 3. So again, we're going to be given an interval for which we're trying to figure out what's the maximum value and what's the minimum absolute minimum value. So let's say this. Say let's find the absolute max minimum values, if any. So the first step, of course, is to find the critical numbers. So how do we find the critical numbers?
We use the first derivative test.
Yeah, you use the first derivative, and then what do you do? You find the first derivative, and when you do so, you get 2x minus 2, and then what do you do?
You factor it out.
You first have to set it equal to 0, and then solve, right?
Right.
And then you can factor, and then you get 2x minus 1 is 0, which means that x equals 1. So I only have one critical number here, right? So this could be a max min, right? Local max or local min. Now, how do I determine that? How do I determine that?
Uh, Testing points.
You can use testing points, or you can use what?
Second derivative.
You can use a second derivative test, right? So you can determine whether the second derivative test will give it a max or a min, right? But I want to figure out what's the maximum, what's the absolute max or absolute min. So this step eventually will not be necessary, but let's just see what x equals 1 is equal to. So let's use second derivative test to determine type of extremum. So what's the second derivative? It's just going to be 2, which is very quick. And I would say, oh, okay, so if I plug in 1, I still get 2 regardless. So what does that mean? That means that this is concave up, right? Because the second derivative is what? Positive. So if I'm concave up and I have a relative and I have a critical number at that point, what happens to the extrema? Is it a min or a max? So if I'm
It's a min.
concave up, what am I? Am I a hill? Am I a hill or a little valley?
Ouch.
Your little valley.
I'm a valley, right? So that means that I am a relative. So there's a relative minimum, right? At x equals 1. Now, how do I know if it's a absolute minimum? So this is where it's very simple. It's not as complicated as other things that we've done. So what we're gonna do is we're gonna find the values, or I should say, find the y values of the endpoints and of the critical numbers. That's it. That's all we're gonna be doing. We're gonna figure out what's the y value of the endpoints. We're gonna figure out the y points of the critical numbers, and then we're gonna compare which one is the biggest and which one is the smallest. And that's the general idea. So look at the endpoints. What's my first endpoint? My first endpoint here is -2. So let me just say these are my endpoints, right? These are the endpoints of interval. So when x equals -2, how do you get the y value? Well, you have to plug it in. x squared minus 2x, right? So this would be negative 2 squared minus 2 times negative 2 minus 3. So I get 4 plus 4 minus 3. 8 minus 3 equals 5. So that's going to be my endpoint, my y value, 5. Then I'm going to compare. It's the first endpoint, right? The second endpoint is x equals 3. Plug it in again, so I get 3 squared minus 2 times 3 minus 3. And I get 9 minus 6 minus 3. And I get 0, it looks like. So those are my endpoints. So I did my endpoints, but now I want to look at the critical number. And I only have one, so that's good. So my critical number is x equals 1. So again, what do? I plug it in, right? Y is equal to 1 squared minus 2 times 1 minus 3. So I get 1 minus 2 minus 3, and I get negative 4. So then what's going to be my absolute max? Not the relative max. What's my absolute max?
5.
Oh, whoops. Yeah, 5. Sorry, Andrew. 5 is my absolute max. Why is it my absolute max? Because it's the biggest y value that we see. And then what's my absolute minimum? What's my absolute minimum, guys?
0.
No. Well, look at all the boxed numbers in the green. What's the smallest?
-4.
Negative 4. So because of that, will be called our absolute minimum. So what's the idea? The idea is to compare the y values of the endpoints and the critical numbers and the highest of such values will be known as the absolute maximum. And the lowest of such values will be known as the minimum, as the absolute minimum of such values. Absolute minimum on the specified interval. So in this case, we're going to care a lot about the interval that they give me. So then we would say, um, we would say the absolute maximum of my function from on the interval -2 to 3 is 5, and the absolute minimum on the interval from -2 to 3 is -4. And let me see if I can hope you see that a little bit clearly. So if I were to graph this, right? If I were to graph x squared minus 2x minus 3, this is what we would get, right? A parabola. So let me graph this. And our intervals from -2 to 3. So -2, if you look at the graph, -2, the y value is 5. That's my y values. And my x value, they go to 3, right? My x value 1, 2, 3 is right here. And then I have a minimum here, a relative minimum here at -4. So then if I graph this, if I sketch the graph, I get something like this. So then isn't it obvious as to what's the maximum on this interval? I don't have the rest of this function. I don't have the rest of it. I only have a piece of it. I only have a piece of it. So this is the graph. This is the graph. The graph of y equals x squared minus 2x minus 3 on the interval -2 comma 3. That's what this graph is. And then what's the maximum? Well, this is the maximum here. This is absolute maximum. Of 5 when x equals -2. And then what's the absolute minimum? Well, it's this one right here. It's the relative minimum, right? It's also a absolute minimum. So this is an absolute minimum value of -4 at x value being 1. So does this make sense, guys? We're looking for the absolute max, absolute min by comparing the y values amongst one another and seeing which one is the biggest on the interval. So we only care about two things. We care about the interval, the endpoints. We care about the critical numbers that exist within that interval. Compare the y values of the endpoints. Compare the y values of the critical numbers. See which one is bigger. The biggest is the absolute max. The smallest is the absolute min. And then in case closed. Okay? Any questions about this, guys? Alrighty. So let's see a few more of these. So let's say if I have something like this. So I have g of x x cubed plus 3x squared minus 1, and it's going to be on the interval -3 to 1, -3 to 2. So I want to find, again, find the maximum min values. Find maximum, sorry, absolute maximum. on the given interval. So what's the first step? What's always the first step?
He's
First
going to find
derivative.
a derivative.
Find the first derivative, right? So my first derivative, I want to find it, and I want to set it equal to 0. So g prime of x
Plus
is
2.
3x squared plus 6x equals 0. So then I set it equal to 0, and I try to solve for x. I factor out the 3x. I get x plus 2 equals 0, and now look what I get. I get x equals -2 and x equals 0 as
Critical numbers.
my critical numbers. That's right. So there we have it. We have our critical numbers. Boom. Okay. Then what do I do?
You can get the second derivative.
Actually, like I said, we won't need to do that any longer because all we're trying to figure out what's the max and min, right? Absolute. So the key word here now is absolute. I'm looking for the absolute max or minimum. So these two
Mm,
guys, we could find what they are, right? We can find them whether they're relative max or min, like whether they're little hills or valleys or so and stuff and such. But we don't need to know that to figure out whether it's the absolute max or min. All we need to do is compare the y values of those critical numbers compared to the y values of the endpoints. And that's it. And see which one's the biggest, which one's the smallest. And then we would be able to determine whether it's an absolute max or min. It's that straightforward. So we don't have to do like the whole first. We could, but we don't have to for this.
Oh, we're comparing the critical numbers y value to the y value of the n. Okay, I got it. I got it.
Right. So then one of them has to be the biggest, one of them has to be the smallest. And
So
then
then
whatever that is, then we say that's what it is. You see what I'm saying?
So we just plug in from now on.
We're just plugging in.
Okay.
Yeah.
negative
So
3.
so then we would say, okay, let's look at the endpoints, right? I'm just separating this up a little bit. So just look at the endpoints. So the first endpoint that I got is -3. So what happens when x equals -3? I want to find a y value. Well, the y
9.
value I can plug in, right?
9
I
times.
get -3 cubed plus 3 times -3 squared minus 1. -3 cubed is -27 plus -3 squared is 9. Right, this thing is 9. So 3 times 9 is 27. And I'm subtracting by 1. So the -27s, they cancel and I get -1. So that's the y value when my x value is -3. And I'm just going to leave that for now. Then now the second x value is the rightmost endpoint, which is 2.
2.
So when x equals 2, what's my y value? Well, y value equals 2 cubed plus 3 times 2 squared minus 1.
4.
This
12.
is 2 cubed is 8.
7,
This is 3
8.
times 4, right? Which
2,
is
6,
12 minus 1.
20.
8 plus 12 is 20 minus 1 is 19. So 19 is the y value associated with the endpoint of 2. Okay? Now let's look at the critical numbers. I'll have two of them, so I have to take care of
8.
both of them.
20.
So what are my critical numbers?
19.
My critical numbers are when x equals 0. That's one of them.
0, 0, -2.
0 and -2. So what happens when my x equals 0? What's my y value? Well, 0, I cube it plus 3 times 0 squared minus 1, and I get -1. Huh. It's a repeated y value. And then
Okay.
I get x equals -2. So y is equal to -2 cubed plus 3 times -2 squared minus 1, and I get -8 plus 3 times -2 is, I get 3 times 4 minus 1. This equals -8 plus 12 minus 1. So this here becomes 4 minus 1, which is 3. So all I have right now are the y values for the endpoints and for the critical numbers. And then all I have to say is what's the biggest? Well, look at all the boxed green, and the biggest
The
19.
end the endpoint
is one of the endpoints, which is
219.
at 19. So this is going to be my absolute max. This is called an absolute maximum, but of course, it's only on the specified absolute maximum on the interval -2 to 3. Remember, it's important. The endpoint is the interval is what specifies the maximum. It's the endpoints. And then the minimum, actually, there's a tie, right? There's a tie at the endpoint and at the critical number. They both reach the same minimum. But the whole point is what's the minimum value? So it's okay if they repeat. So this is an absolute minimum. It just so happens that it does on this interval.
Okay. When you're finding out the absolute minimum or maximum, you don't necessarily need the x value. You just need the y value.
Yeah, because we're looking for the absolute minimum value.
Okay.
Yeah. When we talk about minimum value or maximum value, we're looking for the y value. That's why I'm specifying we're looking for the y values of the endpoints and the critical numbers to see which one's the maximum, which one's the minimum. Because we care about what's the output of the function. What's the maximum output? In other words, what's that maximum y value? What's the minimum output? In other words, what's the minimum y value? So when we talk about values, we talk about y values. So this is an absolute minimum value. This is the absolute maximum value of my function on the interval -2 comma 3. And and let's just graph this just to give us a better sense of assurance here. So if I x and if I raise this to the third power plus 3x squared minus 1, what do I get? You see? So my interval is -3 to 2. So as you can tell, 2 on this graph, 2 is all the way up here, right? The y value is right here, it's 19. It's going to be the maximum y value on the interval -3 to 2. -3, right? And at -3, what's my minimum? My value here is the same thing as this value down here, -1. It just coincidentally they're the same. Not always, but it just coincidentally. But what do we care about? We care about the y values. So what's the minimum y value on this interval? -1. What's the
-1.
absolute maximum y value on this interval? 19. Okay? So that's the way this goes, guys. That's the way it goes. Critical numbers, endpoints, critical numbers, y values, which is the biggest, maximum, absolute maximum, which is the smallest, absolute minimum. Okay?
Okay.
Straightforward, right?
Yeah.
Okay, good. So let's do the same thing for something that looks like this. So what if I got 1/2 x to the fourth minus 2/3 x cubed minus 2x squared plus 3. And this is on the interval -2 to 3. So what do we say about this?
It's gonna be the same thing. Take the derivative.
Same thing, right? So I want to find the first derivative. This is wash, rinse, and repeat type of deal, right? So first derivative. So what's going to be my first derivative?
4x
So I bring down the 4 with the 1/2 and makes it into a
2
2x cubed, right?
x
Bring
to the
down the
third
3. This becomes minus 2x squared minus 4x. Set it equal to 0. I can factor out a 2. I can factor out an x, and I get x squared minus x minus 2 equals 0. I can factor out the quadratic a bit more, and I get x minus 2, x plus 1. There's a 2x in front. This equals 0. And what do I get? I get that x equals 0, x equals 2,
yeah.
x equals -1. So I have a total of 3 critical numbers. So these are my critical numbers. And now what do I do? Compare all the y values. So then let's look at the endpoints first, and then I'll take care of the critical numbers. So my endpoints here are -2, x equals -2. So what's my y value? We'll have to plug it into my function. So I get 1/2 times -2 to the fourth minus 2/3 -2 to the third minus 2 times -2 squared plus 3. And then what do I have? I got 1/2. -2 to the fourth power will be +16. -2/3 times -2 to the eighth to the third becomes a -8. This becomes -2 times negative. So -2 squared is +4 times 2 is -8 plus 3. So we're going to have like a fraction at the end. 1/2 of 16 is 8. This is +24/3, right? No, sorry, 16. It's +16, and this would be -8 plus 3. The good thing is the -8 and the 8 cancels out. So I got 16/3 plus 3. If I write this as a single fraction here, I can write this as 9/3, which equals 25/3. And you can write this as a mixed number if you want. 3 goes in 25 8 times. This is 8/1/3, or this will be 8.3 repeated. So either way, as a fraction, as a mixed number, or as a decimal representation, this is my y value when my x value is -2. Okay, so that's that. That's the leftmost endpoint. Now let's look at the rightmost endpoint when x equals 3. So what happens when x equals 3? Plug it in again. F of 3 is equals what? This is 1/2 times 3 to the fourth minus 2/3 times 3 to the third minus 2 times 3 squared plus 3. This is 1/2 times 81 minus this is 2/3 times 27 minus 2 times 9 plus 3. So I'm going to leave this as 81/2. The 3 goes into 27 9 times. 2 times 9 is 18. -2 times 9 is 18 plus 3. So this is going to be equal to -36 plus 3. This is 81/2. And this will be 81/2 minus 33. I can rewrite this as 81/2 minus 66 over 2. And then over 2, this will be what? This will be 15 over 2. And you can write this as 2, oh no, as 7.5. So that's my y value when my for my two endpoints. So one is at 8.3, the leftmost endpoint, and the rightmost endpoint is 7.5. Okay, so I found the y values for my endpoints. Are we all in agreement? Yes, no, maybe so.
Yes.
We're good, okay? All right. So now let's move on to the critical numbers. We have three of them. We have three critical numbers. So we have the first one is x equals what? X equals 0. That should be relatively simple. When I plug it in, right? I plug in f of 0 into everything, all the zeros. All the x values become zeros, and I'm only left with 3. So that's a quick one. So f of 0 is 3. So that's going to be my y value. Okay. And then what's my x value? My x value will be, next one will be 2. So y equals f of 2. So again, this is 1/2 2 to the 4th minus 2/3 times 2 cubed minus 2 times 2 squared plus 3. So this is equal to 1/2 times 16 minus 2/3 times 8 minus 8 plus 3. So then I get 8 minus 16 over 3 minus 8 plus 3. And I get negative 16 over 3 plus 3. Negative 16 over 3, I can write this as 9 over 3. And what do I get? I get negative 7/3, which is the same thing as saying 3, negative 3 and 1/3. No, not negative 3. Sorry, negative 2. Negative 2 and 1/3, which is the same thing as saying uh, negative 2.3 repeating. So it's going to be a repeated number. So that's the y value when my x equals 2, when my x value equals 2. And then lastly, when x equals, so I got 2, negative 1. So what happens when I get x equals negative 1? My y value is what? I get 1/2 negative 1 to the 4th minus 2/3 negative 1 cubed minus 2 times negative 1 squared plus 3. So this becomes 1/2 minus 2/3 times negative 1. So this becomes a positive 1, positive 2/3. Then this becomes minus 2 plus 3. Minus 2 plus 3 is really just plus 1. And then I have to make these all the same denominator in order to add these up. The least common multiple between 2 and 3 is what?
6.
6. So then I can write this as what? 3 over 6 plus 4 over 6 plus 6 over 6. And this will equal 3 plus 4, 7 plus 6 is 13 over 6. Which is the same thing as saying 2 and 1/6. Which if you know your decimals for fractions, this would be 2.16 repeating. Okay, so this one, as you can tell, took a little bit more out of us, right? Because of the computation, it wasn't as simple nor as clean as the other ones. But regardless, these are all my y values. So looking at the y values, what is the largest out of all of these?
8.3.
8.3.
Repeating 3.
Right. So we say this is my absolute max. And then what's my absolute min? Out of all the y values, the smallest one is,
Negative 2.3. Repeating.
yep, this is my absolute minimum. Okay? So that's how you find your absolute max, absolute min. Find the y values of the endpoints, find the y values of the critical numbers, and compare. Compare which one is the biggest, which one is the smallest. And once you're able to do that, you found it. You found the absolute max and absolute min. Um, and let's see what this would look like if I were to graph this. So I got 1/2 x to the fourth minus 2/3 x to the third uh, minus 2x squared plus 3. So this is what I would get. The minimum, as we said, was negative 2.3, which is exactly what we said. That's my absolute minimum. So as you can tell, it's the absolute minimum because it's the smallest, it's the most, it's the lowest part of my function. And then I'm only looking at the interval, and the interval that I'm in is negative 2 to 3. So only within this window between negative 2 and 3, I can't look at anything else from negative 2 and 3. So then, as you can tell, we do have a relative max here, right? 0, comma 3. We do have a relative min here, negative 1, comma 2.16, as we found, but they're not the smallest nor the largest. They're just locally the smallest and largest, local, in the local region. So then we had to look at the endpoints, and then my endpoint was negative 2, right? And it looks like it's going to be somewhere exactly what we found, right? At negative 2, we found that it would be 8.3. And at 3, what was it? At 3, it was 7.5. So what's going to be bigger? The 8.3 one. So that's why on that interval, 8.3 is the biggest, and negative 2.3 repeated is the smallest. So any questions about absolute max and absolute min?
Just a side note. So
Yeah,
the critical number 0, well, the point 0 comma 3 would be a local maximum.
that's right. So then if you
Okay.
want to really, give everything, all the information out, yeah, then you would say, well, this here, it's not a max, it's not an absolute max, but it is a local max for sure. And then this one here would be a negative
Lo-
1. This would be a local min, right?
Mm-hmm.
Right.
Okay.
So if we cared about all of the different kinds of extrema, then yes, we would say local max, local min, absolute max, absolute min. But for now, we just care for the absolute max and the absolute min. Okay. So good. Very good. Very good. We're getting more acquainted with this kind of task, right? Now, uh, what if my function is not a polynomial anymore? What if I have something like this? 4x plus 1 over x on 1 comma 4. So this is when my function is no longer a a polynomial. So polynomials are all of these functions that we've done before this example. Polynomials are the functions whose exponents are nice whole numbers. But for example, in our new example here, we have a function whose x value has a negative exponent. So the moment you have a negative exponent, right, I can rewrite this as x to the negative 1. The moment you have a negative exponent, it's no longer a polynomial. So then it's going to look a little different. But what's the first step? Of course, first derivative. So now the question is, what's the derivative of 4x plus 1 over x?
Don't you have to do a little bit of rearranging?
I would have, well, yeah, I only have to do one extra thing, right?
Move the x to the numerator.
Right. I would rewrite this, so then rewrite f of x as 4x plus x to the negative 1 power, and then I can find the derivative, which would be what?
4 plus um no 4 minus
Yes, it would be in the
uh
negative one.
x to the negative 2.
Right, because of the power rule, right? The power rule states you put the exponent in front, and then subtract by 1. So then just to make this a little nicer, I would write this as 4 minus 1 over x squared, and this equals 0. Okay. And then what do you do after that? You try to solve, right? How do I solve this? So now I want to solve for x. Uh-huh.
What?
How do I solve this
We're
equation?
gonna multiply. You're gonna subtract 4 from both sides.
Okay, so if we do that, I get negative 1 over x squared.
And then you're gonna solve for uh x squared. So you're gonna multiply both sides by. Wait, no. Gotta.
Yeah, keep going. So I
Oh,
want to get x squared, right? But x
so
squared right now is in the denominator. So then what should I do?
you gotta get it in the numerator. So
Yeah,
you're gonna multiply. Okay, yeah. Wait, I don't see how multiplying. Wouldn't that put it on both sides?
if you multiply x squared on both sides, what happens? Look, if I multiply x squared on both sides, look what happens.
When this side
The
cancel?
x squares here cancel, don't they?
Yeah, but then you have it on the side that you don't want it on.
Sure.
Oh, and then you just gotta add
No,
4 to this.
and then you gotta divide.
Oh, true. Okay, I'm
Divide
so
by negative 4, right? So
yeah.
this is a little game here we're playing. So x squared equals positive 1/4, which is good.
Yeah,
Now
that
all
makes
I have to
sense.
do is what? Square root.
Yep.
When I take the square root, I get x by itself, and then I have to do the plus or minus because of I took the square root of something squared. So it's plus or minus what? What's the square root of 1/4?
1 squared.
The
1,
square root
2.
of 1 over the square root of 4, which is 1/2, right?
Yeah, 1/2.
Plus or minus 1/2. So then what are my
Okay.
critical numbers? My critical numbers is x equals 1/2 and x
X
equals
equals negative
negative
1/2.
1/2. So these are my critical numbers.
Okay. Yeah, yeah. I got a little lost there. I looked at it like you're supposed to be done after the multiplication of dx squared. I was like, what?
Yeah, so you see, these things get a little complicated because the functions get more complicated. The
Yes,
function,
very true.
when you have polynomials, they're usually very simple. You power rule, factor things out, things work out very nicely. But then when you have things that are no longer polynomial, you have to be a little more um, aware of how to use the algebra to solve. But then
Yeah.
these are my critical numbers. Great.
By negative makes it a positive.
Isn't there another critical number? But no.
Squared.
The issue is that 0 So the problem here is at 0, note. So make a note of this. Note, x equals 0 is not in the domain of f of x. So it's always important to figure out the domain. The domain here is everything that's not 0. Because
Oh,
if it does equal 0, then what would happen? This here would be 0, but 1 over 0 would be undefined.
yeah.
So x equals 0 is not in the domain.
And
This
we never
is,
had to do that before because we were dealing with polynomials, right?
yeah, we didn't have to worry about that. Now that we have things that are not polynomials, the domain is a crucial part because we didn't worry about that in polynomial world because all polynomials have domain that are all real numbers. So everything is nice. Everything works. But here, x equals 0 does not work because when you plug it in again, I get 0 in the denominator, which is undefined. So this could have been, remember the critical numbers are numbers that make the first derivative equal to 0
Or
or
undefined.
undefined. So this is also undefined when x equals 0. However, my function is not defined when x equals 0. So I don't have to talk about x equals 0. Do you understand?
So from this point, would you just start plugging?
Yeah. From this point, once I have that, I just go to the second step and I look at the different y values for the endpoint. So then I got my endpoint here.
4 1 over 2
So my first
minus
endpoint
2
is x
plus
equals 1. So then what's my y value? I get 4 times 1 plus 1 over 1, right?
2,
So I get 5.
2.
I get 5. And my second endpoint, is it 4? Yeah,
What?
it's 4.
Professor,
Yeah.
how did you get 4 times 1?
Yeah,
Oh, okay. You took the
I plugged it in.
Okay, yes. Okay, I plugged in just something different. That's
So
all.
this is 4 times 4 plus
Yeah.
1 over 4, right? I'm just plugging it into my original equation. And I
Yeah.
get 16 plus a fourth, which is the same thing as saying 16 plus 0.25. So my answer would be 16.25. The reason why I write it as decimal is because it's easier to compare it than with fractions. Fractions is not that easy to compare as opposed comparing them as decimal. So that's that. And now let's look at the critical numbers. So the first one, I'm gonna write x equals negative a half. And again, I only care about the y value. So this becomes f of negative a half, which is 4 times negative a half plus 1 over negative a half. This becomes negative 2 minus 2, which is
4.
negative
Negative
4.
4.
And then my second critical number is 1 half. So y is equal to f of a half, which is equal to 4 times a half plus 1 over a half, which is 2 plus 2, which equals 4. Okay. I found all the y values for the points that I care about, the endpoints and the critical numbers. So then you say, hey, what's the biggest?
16.
The biggest is 16, so this will be known as my absolute maximum. And then negative 4 will be my absolute minimum because that's the smallest. And of course, it's going to be on the interval, absolute maximum on the interval 1 through 4. And this is the absolute minimum on the interval 1 through 4. And we're done. And just to give us a bit more of a visual here, what's 4x? What does it look like when I graph it? 1 divided by 4. So when I graph it, this is what I get. Oh, whoops. That's not what I meant to say. X. You see that? It looks a little strange, right? It's like two pieces of, it's like two different pieces. So the 1 through 4, right? 1 through 4. At 1, what is the, let me see. At 1, sorry, this is 1 through 4. So I'm not even looking at this piece over here. I'm looking at only this top piece. So 1 through 4, what's the smallest value? Wait, what interval am I on again? Oh, I'm on 1 through 4. So pardon me. So do you see how that changes? What does that change?
The critical number we're using.
It changes the absolute minimum. So in actuality, right? If I amplified my interval a bit more, it would be -4.
It's
But
4
yeah,
because we're
right.
not looking at the negatives at
We're not
all,
looking at the x values that are on the negative side of things. So we would
or
say,
anything lower than 1, pretty much.
right, anything lower than 1. So we would say, we would disregard this. We disregard because x equals -1/2 is not in interval 1 through 4. So no way, guys, we have to just disregard this completely. We don't care about this. So then what's the smallest? You see how this changes? This is the smallest now. So this is the absolute minimum. So always, just in case, guys, always use your graphing calculator to give you the sketch of what the graph looks like. And so then now it makes more sense, right? Between 1 through 4, what's the smallest? It is gonna be what?
4.
4. Wait, let me see. Is it 4? Yeah. No, actually, it's not 4, guys. Do you see why? It's for the same reason. 1/2 is not in the interval between 1 through 4.
Oh my god.
So these numbers, we don't care.
So it's 5.
It's 5, yeah.
It's just the
It's
endpoints.
the thing is, the intervals what we care about, right? We care about 1 through 4.
So we pretty
So
much did the critical numbers for no reason.
no, we found the critical numbers, but we didn't need to find the y values of the critical numbers.
Right, right,
That's what you
exactly.
meant. Yeah.
Yeah.
So then we would say we would have to be a little more perceptive. We would say, hey, look, these guys, these critical numbers are not in the interval 1 through 4. So because of that, we do not need, no need. There's no need for this. No need to find y values. We did it anyways. We don't need them because the interval that we're considering does not include them. So we don't care about them. So all we care about are actually the endpoints. So this is going to be my absolute min. So that's why it's important, guys, to always keep in mind the interval that's specified. This only makes sense if you specify an interval. It only makes sense to find the absolute minimum and absolute maximum if you have a specified interval. If you don't have a specified interval, we normally would not be able to always talk about absolute max or min. So it's important, guys. All right, it's important to know your interval. Okay.
If the interval was to start at -1/2, then our original answers would be correct.
If yeah, if yes, if you
Okay.
would say include the interval from -1 to 4 instead of 1 to 4, then
Okay.
then clearly you would see, right,
Okay. That was like a tricky type of question.
is that these questions do become trickier as your functions they become something that are not polynomials. You see, look, even just graphing this, it's a little strange. What kind of shape is it? I don't know what type of shape it is, you know? So this is when things get a little strange. The world is a lot strange place than you think. Okay, so I'm gonna give you like two more of these strange ones, and then we'll see some different more applications of this, because that's really what we're headed towards. We're headed towards how calculus is really applicable to quote unquote real world problems. Calculus is so important because it solves many real world. It explains real world phenomenon, but it also solves real world problems. Pardon me. Okay. Let's look at this. So if I have my function 1/2 x squared minus 2 rad x, of course. Now we have these radicals, right? These radicals, these pesky little radicals. Okay, so the first step is again first derivative. So what's my first derivative? So what am I gonna have to do first? I'm gonna have to rewrite f of x first. And how would I rewrite f of x? Why would I do that? How would I rewrite the square root of x? I would write it as what? X to the 1/2. Thank you, Fujing. X to the 1/2. Okay, good. So now that helps because now I can find the derivative, right? The derivative of 1/2 x squared is x minus, then you can take out the 1/2 in front of the 2. That becomes 1. And you bring down, you subtract, right? You get 1/2 x. You have x to the negative 1/2. And this equals 0. Okay, now what? How do I solve this? You see how things get a little complicated now? How do we solve this? A little crazy, right? Looks a little scary. Well, I can rewrite this as x minus 1 over the square root of x equals 0. And then what? Well, there's several things I can do here. I can um I can rewrite this as x equals 1 over the square root of x. And then I can square both sides and I get x squared equals 1 over x. And then I can multiply both sides by x. So this is where your algebra has to be really good. X cubed minus 1. I mean, x cubed equals 1. So what does x have to equal? 1. So x equals 1 is a critical number. And just in case you guys don't just want to check, if x equals 1, if I plug it in here, what do I get? 1 minus 1 over square root of 1. But 1 over the square root of 1 is 1. 1 minus 1 is 0. So this works. Critical number. Now the question is this the only critical number? Remember, critical numbers make my derivative either equal to 0, or it makes it equal to, or maybe not equal to, it makes it undefined. So I found the x value that makes it equal to 0. What happens if I take my derivative and I want to make it undefined? What x value makes this derivative undefined? What's a bad x value for this? And all you have to do is look at the denominator. What makes my denominator equal to 0? It's going to be when x equals what? Anybody? You see, the moment we deal with things that are not as simple as the other ones, right? People tend to like second guess themselves. So what x value, guys, when I plug it in here, makes this undefined? Right, Coco, is 0. If x equals 0, no is no good, right? If I plug in 0, my derivative is undefined. So actually these are my two critical numbers. My critical numbers are when x equals 0 and when x equals 1. I have two critical numbers. And now the question is this part of my domain? Is x equals 0 part of my domain? Well, there's nothing that goes wrong when I plug in 0 here, and nothing goes wrong when I plug in 0 here. So it is in my domain. And x equals 0 also happens to be an endpoint. So your x equals 0 is both a critical number and an endpoint. That can happen as well. All right. So now let's look at step number 2. What are my endpoints? My endpoints is when x equals 0, which is also a critical number. So y is equal to f of 0, which is 1/2 times 0 squared minus 2 times the square root of 0, right? Is that what it is? That's right. And then what do I get across the board? I get 0. Quick and easy. Okay. And now when x equals 3, y is equal to f of 3, which is 1/2 times 3 squared minus 2 times the square root of 3. So I get what? I get 9 over 2 minus 2 square root of 3. So I get 4.5 minus 2 rad 3. And then if I want to find the decimal, I want to find the decimal here. So then I get 4.5 minus 2 rad 3. And I get 1.3. 1.0358 dot 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 dot. So that's going to be my decimal. Just helps me see which is bigger, which is smaller. And then the critical number, because I already figured out x equals 0, I don't have to plug it in again. The only critical number that I have to consider is x equals 1. So when x equals 1, what's my y value? Well, plug it in. And I get 1/2, 1 squared minus 2 rad 1. I get 1/2 minus 2, which is negative 3/2, which is negative 1.5. Okay? And so then on this interval, all my x values, right? and my critical numbers are within the interval. So we're good. So then what's the smallest and what's the biggest? The smallest is the smallest y value is too much turkey, huh? What's the smallest out of these numbers? There's only one that's smallest and one that's biggest. Let's go, guys. Did I lose you anywhere here with the solving? Thank you, Badur. So yes, this is the gonna be the minimum value. Absolute, sorry, the absolute minimum value on the interval 0 to 3. And obviously the maximum would be this guy. Absolute max on 0 to 3. Okay? And then just to make sure we're all on the same page and everything is what I say it is, let's graph it really quick. So I got 1 divided by 2 x squared minus 2 rad x. And if I graph it, look what I get. I get like I get a piece of a parabola, it looks like. And I'm only on the interval 0 to 3. So this is my interval. And what's my minimum value? My minimum value is 1.5, as you can tell. And then what is my maximum? It's let's see, 3. We said it was at 3, right? And 3, we found it to be 1.03. So it's very close, right? It's very close to 1, as we can tell right here. It's very close. So it's going to be something like that. The smallest value is negative 1.5. And again, we're talking about the y values. The smallest y value is 1.5. And the highest y value on this interval is 1.0358, which is a irrational number. Okay, so do we get the idea, guys? Do we get the idea? Absolute min, absolute max. Yes.
Yeah. Lowest
Okay.
point and highest point between an interval.
Okay. See, so that's clear, right? Correct. All right. I'm glad. I'm glad you find this stuff to be simple. Now, I'm gonna give you some applications to this, and maybe this is when this whole idea comes to life a bit more. And let me ask you this problem. I'm pretty sure most of you have seen it some way, somehow, especially when we talk about maybe some high school mathematics when you're looking for the when you're trying to study for the SAT. I think this problem would come about a bit. I don't know if you've seen this before. So a stone is thrown straight up from the roof of an 80-foot building. The height of the stone in feet at any time at any time t in seconds is given by, so of course we're given a quadratic. And the question is, what is the maximum height that the stone reaches? Have you guys seen a problem like this before? Is this right? Like when we talk about quadratics, it's classic. That's right, Santiago. It's a classic problem. Now, do you guys remember how you would solve this without calculus? In physics, that's right, Coco. That does appear in physics. This is calculus comes from physics. So, do you guys remember how we would do it? Yeah, you would have to find the vertex, right? You would have to find the vertex of your parabola by finding the axis of symmetry. So it was a long step process, right? You first find the axis of symmetry, plug in the axis of symmetry into your function, find the y value, and that y value would be the corresponding height. But do you see how calculus simplifies that a bit? Because I don't need to find the axis symmetry any longer. And I don't need to plug that in any longer like that. How would I do so? What would I use instead of the axis symmetry now that we know more about derivatives?
First derivative.
The first derivative works, huh? So what happens if I find the first derivative? What is the first derivative? What is that able?
The
What am I trying to figure out when I find the first derivative? So what is the first derivative anyways? Negative 32t plus 64. Now, what do I do with my first derivative? I do what with it? Set it equal to 0. If I set it equal to 0, I solve for t and I get what? I get negative 32, factor out, I get t minus 2 equals 0. So then what do I say? T equals 2 is a what?
Maximum height. A critical number.
Critical
critical
number.
number.
The critical number indicates what? It could be a local max or local min, right? Now, how do I determine whether it is either a local max or local min? I can use a second derivative test. So h double prime of t is what? Negative 32. Always. Doesn't matter. Doesn't matter if I plug in 2 here. I would always have a what? Concave down. This is always a concave down function. And we should have known that from the beginning because it's a parabola that opens downward. It's concave down, so this indicates that what? This is a concave down means
Maximum.
there's a local max, right? A local max. Now, what are we looking for? Are we looking for local max or what? Do we just care about the maximum that's locally maximum, or are we trying to figure out the absolute maximum? So in this problem, we're looking for what's the highest it is. What is the highest that the stone can ever reach? And what do you realize? This local maximum is indeed what? This local maximum is indeed the absolute max. Why is that though? How do we determine whether something's an absolute max? We compare it with what? We compare it with the endpoints, but we don't have any endpoints, huh? So how does that make this any different? So now we'll see how this gets a little more complicated because they don't give us the endpoints. So how can we be so sure? Well, we have to consider the context of the problem. What are we dealing with? We're dealing with a stone that goes up and it goes down. But we're looking at the height, and the height is given from the distance between the stone and the ground. So can the height ever be a negative number?
No.
No. So there's actually a restriction upon this height function that was not specified before. That's right, Santiago. The y-intercept is 80. You can think of that as being on the roof of an 80-foot building. When you're on the roof, right, your y-intercept is 80. It means that your function starts at 80 because you're already the stone is already 80 feet above when you initially throw it. But then after you throw it, it reaches a certain height, a maximum height. And then it goes all the way down until it hits the floor, which is the height of 0. So there's a restriction that we didn't that they didn't specify to us, but that we had to figure out on our own. The restriction is that the height has to be bigger than or equal to 0. That's my restriction. So what's going to be my interval? What's my interval? My interval will always start at 0 first. So my t value has to be bigger than 0 because I can't go in negative time, right? We're not dealing with negative time. We don't deal with -1, -2. So we can't talk about that. T has to be bigger than 0. But then at the same time, your height can never be negative. So when is your height 0? When does it ever reach 0? So that would be your other endpoint. So then let me just graph this and then we'll see, we'll have a better understanding of it. So we get a -16 squared uh, plus 64 plus 80. So if I graph this, look what I get. So the graph, see, you see, oh my goodness. The graph of this function, you see this graph? It's a parabola. It's very thin, right? But the context of my problem never includes to the left of 0. It starts from 80. And then it goes up, it reaches a maximum, and that's the maximum that I want to figure out. And the maximum actually is 144. And then what happens? The stone falls. It falls and it hits what? It probably hits the floor. And hits the floor exactly at 5 seconds. So my interval is really between 0 and 5. Even though they don't tell us this, this is my interval, guys. It's 0 to 5. Why is it 0 to 5? Because h of t on this interval is uh, greater than or equal to 0. So in reality, I only have to test the endpoints at 0 and 5 and at 2. But obviously at 0, what happens? My endpoints, right? When t equals 0, what's my height? It's 80 feet. This is my y-intercept. And then when my t value is 5, what's the height? It's 0 feet. And then my critical number, what's my critical number? T equals what? T equals 2. So what happens when I plug in 2? I get negative 16 times 2 squared plus 64 times 2 plus 80. I get negative 16 times 4 plus 128 plus 80. I get negative 64 plus 128 plus 80. Negative 64 plus 200 and 208. And if I subtract that by 64, I get 144. Right? And then what do I care about? I only care about the maximum height. And the maximum height is 144. So then the stone reaches a maximum height of 144 feet. Done. Hmm. Okay? So using calculus now, we're able to figure out the maximum and minimum of functions. And this is useful when the functions that we're dealing with model or represent a physical or economic phenomena. It doesn't have to be physical, it could be financial, it could be about population growth, it could be several things that we can model through functions. So that's why calculus is really just a study of functions. And why do we care about functions is because a lot of things in this world can be modeled by functions. So if we have a good understanding of functions, we have a better understanding of the world around us. That's why we talk about functions so much.
So,
Like
Professor, we found like t equals 5 only because you used the help of a graph to find out where the endpoints are.
really, it's because how would we get t equals 5 without a graphing calculator? Without a graphing calculator, you would have to set
Original
uh,
function to 0,
original function equal to 0 and then solve a quadratic.
and that would eventually give us 5. Okay.
That would give us 5 because you can factor out the negative 16. This is just a nice function that you can factor out to 16. And then you would get what? You would get t squared minus 4t minus 5. So then you would get t equals negative 1 and t equals 5 at the end or something like that. But the idea, guys, is how do I know? Why did I know to do that? It's because I understood the context of the problem. So then this is where you have to come in with the understanding of the scenario that you're dealing with. I'm dealing with a stone being thrown up and down. So there's a certain height that it reaches, and the minimum height has to be 0. You can't have negative. And we're also not dealing with negative time. So time, when we talk about something being modeled with time, 0 is the first interval, always. So that's why our endpoint started with 0. because this is the initial time. This is when I start. This is when my rock is being thrown for the first time. It's exactly at 80 feet above the ground. Then what happens? It goes up, whoop, 144, and then it dips. Whoo, it falls. It falls all the way down until it reaches 0 feet. But it's not going to go beneath, right? It's not going to go negative 5 feet unless it's a huge, it's an immensely dense rock that just breaks through concrete when it falls. So then these are assumptions that we make. So see, all of these things that we've just discussed is the kind of thinking that you would be required as you get into more complex problems that are related to real world, right? You're gonna have to make assumptions about things, um, so that all of this works out. Because of course, the real world is never this clean, right? It's never this predictable, and that's why we need more experience with these kind of problems, and we need more, maybe more advanced tools mathematically or computationally. But of course, this is when we're talking about more advanced stuff. But for this now, I'm just saying, I'm just trying to like give you guys a bigger picture, right? Because like, why do we do all of this stuff? It's because we have other problems that we want to try to solve. They get more interesting. Okay, so that's something that you've seen, and now you've seen before without calculus, and now you've seen it with calculus, which is cool. Okay, so let's see something else. And let me just ask, do you guys like this kind of problem to solve, or do you like the previous problems that we've just done with like finding the absolute minimax? Which problems do you guys prefer doing? Do you guys prefer doing this kind of problem where you have to like think about the context of the problem, or do you just prefer, hey, just give me the problem and let me just
I much prefer the straightforward questions we were doing before.
Yep, the
Yeah,
previous
right.
one.
Like even though this one seems a bit shorter, it's just the other one has a structured formula where it's
okay.
like,
So you guys
like
prefer just plugging and chugging in.
yeah, yeah, just a straightforward, like this is the formula, this is the recipe, cook it, you know?
You kind of have to wiggle your brain for this one. The other one, you just follow
You
the
just follow
steps.
the steps. So you guys
Yeah.
prefer the following step procedure, and that's it. Just move on.
Yes, much prefer that because I could replicate that. But this time, like this, if you mess up the setup, though you know how to do all the steps, if you mess up one thing, then the whole pool is tainted.
Okay. No, it's interesting. I just want to know. I want to know what you guys where you guys' head is at. Um. Okay. Let me give you another one. Like, let me see. So many to choose from here. Yeah. So let's say I do this. The altitude in feet. Yeah, I appreciate your honesty anyways. Don't worry. You can be as honest as possible. By a model rocket T seconds into the into flight is given by is given by the function h of t, which is negative one third t cubed plus 4t squared plus 20t plus 2. And see here, they say t is greater than or equal to 0 because it makes sense. Your time starts at 0 and it goes on for an indefinite amount of time. Of course, this is a model of your flight. And then again, the question is find the maximum. Find the maximum height of of the rocket. So I want to find the maximum height. Okay. And now what? What's the first thing I have to do?
Find the critical number.
Find the critical number. That's right.
First, first derivative.
First derivative. So you guys are experts now. First derivative. What's my first derivative? H prime of t is what? Negative t squared plus 8t plus 20. Set it equal to 0. What do I get? Can I factor this? I can, right? How do I factor this? Yeah, so I can factor out the negative and I get t squared minus 8t minus 20 equals 0. And then I get t minus 10 t plus 2 equals 0. And I get t is equal to negative 2 t equals 10. These are my what? My critical numbers, correct? Okay. But which one of these do I include both? Do I need both?
You don't need the negative
I don't need a negative. Why?
because time can be negative.
Because I'm not even, yeah, that so do you see the big picture behind this? So mathematically speaking, this would be important because it's a critical number. However, it's not important for the problem because the time does not include negative time. It makes no sense to include it. So then we say this is uh not regarded due to the fact.
It would pretty much, it means like -2 time wise before it even took flight.
Right, but
We,
that
we,
makes
we no sense at all.
it has no relevance to the problem. Like
Right.
that whole, like, so the graph of that's why, like, you can, this is what you can think of now. You can think that models, they're not perfect, they're models. They just give you a pretty good idea of what may happen, but mathematically speaking, this negative 2 has no relevance to the actual physical occurrence of this, or the trajectory of this flight. It has no real meaning to it, so we don't even consider it. So models have limitations. Models have, you know, uh, um, there are things that don't completely represent the real world, not everything. But at time equals 10, that works out. Okay. And then what? And then I say, hey, then let me see what this looks like. Is this a relative max or relative min? So then what would we say? Second derivative? We could do second derivative or the first derivative test. But the second derivative test, I think it's a little bit just quicker because we already found the first derivative. And we can write this as negative 2t plus 8. It's a linear function and plug in 10. It's very simple. So I got negative 2 times 10 plus 8. This is negative 20 plus 8, which is negative 12. What's the idea here? The second derivative is negative, which means that it's what? Concave down. So if my critical number is concave down at a particular point, then we know it's going to be a max. It's a local max. And at t equals 0, what is the endpoint that I have? What is the endpoint? I only have one endpoint, really. T equals 0. At t equals 0, what is my height? If I plug in 0 into my height formula, what do I get? I get 2. This is my initial height. So the initial height of this model rocket is 2 feet above the ground. And then it goes off into space. It goes off into the air. And eventually, it seems to be that it goes up and then it eventually goes down, right? And so t equals what? So the problem is these kind of problems, guys. You have to graph them because sometimes solving them is not always possible. I don't think this one will be possible. So we have to use our calculator for this. This is plus 4x squared plus 20x plus 2. So if I graph this, what do I get? Look at this. You see this? So this is the whole polynomial, right? It goes from negative infinity to positive infinity. But I only care about the fact when it launches the rocket. So the rocket launches when time equals 0. So it's at 2. And then it reaches a maximum. As we said, our time was what? Of 10. And the maximum here, we were able to figure it out, is 268.6 repeated. That's how high it reaches. And then eventually it hits the ground again, right? Where does it hit the ground? At 15.871. So this is really the other endpoint. This is really the other endpoint. Because the rocket will not go to the depths of the earth. Look at this. This keeps on going all the way down. So we're not going to be considering that scenario, right? We only care about the fact that the height of the rocket is above 0. So in reality, my restriction here was what, 15.817? So in reality, my restriction here, my restricted interval is really from 0 to 15.817, dot, dot, dot. Because that is when the height is 0. So I really have another one here, t equals 15.871, whatever, right? And the height of that, 817, sorry, is 0. This is when the rocket hits the ground again, when the rocket hits ground. And then we know the critical number. What's the critical number? When t equals 10. If I plug in 10 into my function, according to the calculator I have here, the height is 268.6. 260.6 repeated feet. And obviously this is the highest height. And so this would be my maximum height. This is the maximum height of the model rocket. So guys, what we're doing now, what this stuff is, right? When we talk about maps, absolute maximum, minimum, when we talk about that in the context of problems, this is called optimization. So the technique, right? Absolute min, absolute max, those are like the techniques. Those are like the smaller concept that when you apply it to the real world, it becomes what's called optimization. So we're trying to figure out what is the maximum of that a phenomenon attains, what is the minimum that a certain phenomenon attains. And this idea of optimization occurs in every almost every facet of our lives nowadays. Make sense? So what's something that we always want to maximize in our lives?
Profit.
Profit, of course. So now the question is, how do we do such a thing? We want to minimize what?
Cost.
Aha. So you see, this is, I know, very basic, but this is what we want to do, right? We want to maximize our profit while minimizing our costs. The problem is that that's very, very difficult to do, right? Because one affects the other. It's not that separate. If you could maximize, you would want to maximize the profit by having zero cost, but that's impossible.
Or by paying less,
Or by what?
you pay less taxes.
Yeah, you pay less taxes, but then you still wanna you're still gonna pay taxes regardless, right? So how low can you pay taxes? How low can taxes be so that you maximize your profits? Well, that's a whole nother story. But the idea is that we already have this kind of ingrained in our lives, right? We want to maximize certain things and we want to minimize certain things. So we want to maximize profits while minimizing our costs. We probably also want to maximize our profits while minimizing the time that we spend, right? Because who wants to be working for making profit, but who wants to be working 80 hours a week or 60 hours a week to do to do that, right? So a lot of financial bankers, right? Like a lot of them, they have crazy hours, right? People do investment banking, right? You guys know better than I do probably. But they spend, from what I've heard, 60, 70 hours. So they're making bank, they're making money.
It's a
100
lifestyle.
hours.
Huh?
A
It's a
hundred.
lifestyle.
Yeah, I mean, of course, right? If that's what you want to do, then go ahead. But eventually that kind of lifestyle, I don't know. Is
You're
it
gonna burn out.
sustainable? Is it sustainable? Like,
No,
would you be able to do that for the next 30, 40 years? Probably not, right? Probably you'd be like, you know what? Probably you could do that in your 20s, in your 30s, maybe in your 40s, but then eventually your body doesn't behave the same. You can't be up for that long. Like your concentration doesn't changes. So then, anyways, but that's what I'm saying. Like, you want to minimize, maximize things in your lives, and it all depends upon what you're into, your disposition, your goals. So let's look at an example where we have to minimize cost. So let's see. So let's say I say, suppose the total cost for manufacturing a certain product is a cost function 0.2 times 0.1 x squared plus 120. Oh my goodness, dollars. Where x represents the number of units sold. Find the level of production that minimizes the average cost. So I want to minimize the average cost, but I want to figure out how many units do I need to sell given this model so that I minimize the cost. So the first thing is, what is average cost? Do you guys remember? Remember, it's like C bar over C. There's like a little line above C. So how do I? What's the formula for average cost? Anybody? Guys, remember it's just the cost function divided by x. So it's gonna be 0.2 0.01 x squared plus 120 divided by x. But of course, this is not pretty in the slightest. So let's make this a little simpler for us. So what if I multiply this out? Distribute. What's 0.2 times 0.01? It's going to be what? 0.002 x squared plus what? What's 0.2 times 120? It's going to equal what? Anybody?
24.
24. And then I can rewrite this as 0.002 x squared divided by x plus 24 divided by x. The x is canceled here. And my average function is what? My average function, cost function, is 0.002x plus 24x, 24 over x. So that's the average cost function. And what am I trying to figure out? I'm trying to find the minimum. The minimum. So then what am I supposed to do to find the minimum? To optimize. What am I going to do? What is it that we're always going to do now to figure out the maximum or minimum of
First
a function?
derivative.
First derivative. That first derivative is so essential. So what's the first derivative? What is the derivative of the cost function, average cost function? Well, the first derivative here would be 0.002. That's easy. And then what would be the derivative of 24 over x? Well, if you guys wanted to, right, you can rewrite this as 0.002x plus 24x to the negative 1. So what happens when I take the derivative of 24x to the negative 1? It becomes what?
Negative 24
Negative 24
to the x to the negative second.
to the second power, right? So I can put that in the bottom. And then set it equal to 0 and solve. So when I solve this, what do I get? I get 0.002 equals 24 over x squared, right? I'm trying to get x, so I put that on the other side. Then I'm going to multiply x squared on both sides if I need to. So I want to no longer have the x squared on the bottom. And I got x squared times 0.002 equals 24. So I'm going to divide this by 0.002. Divide it by 0.002. Oops, too many zeros. So they cancel, and now I got x squared is equal to 24 over 0.002. So then, just to graph this, to calculate this, what do I get? I get 24 divided by 0.002. I get 1200. No, 12,000. So I get x squared equals 12,000. So that means that x is equal to plus or minus the square root of 12,000. So if I get the square root of 12,000, it's 109.54. So this is going to be equal to plus or minus 109.54, and this goes on forever. Now, does the negative, so these are my critical numbers, I have two of them. Does the negative value make sense here?
No.
It doesn't. You don't have negative units to sell. So we negate the negative and we only say what? X is equal to 109.54 units, right? And so then, now what? And then what do we say?
W- would we need to find the concavity of the, or no?
Well,
Or we just plug it in?
if we find the concavity, right? Second derivative test. What do you notice about the second derivative? What would be the second derivative? It would be what? It would be negative. If you take the second derivative, this is 0, and the derivative of this will become what? It will become negative 4. It will be positive 48 over x cubed. But if you notice, it doesn't matter what I plug into x. This will always be positive as long as x is positive. So if it's always positive, that means that what? It's always concave.
Up.
It's always concave up. If you're always concave up and your critical number is concave up, that means that it's going to
It's a
be a
minimum.
minimum,
A local minimum.
a local minimum. But because that's something else we can talk about, it's a local minimum, but it's not only going to be a local minimum, it's also going to be a
Absolute minimum.
absolute minimum.
It's technically our lowest minimum. That's why.
Say that again.
It's because it's our technically it's the lowest minimum.
It's the lowest minimum, which
That's
makes
why.
it the absolute minimum.
Yeah.
That's the only other minimum to speak of
Right. Right. In this situation.
in this situation. That's right.
So we just plug it into the original cost
You plug it
function.
into the original, right, to figure out what is the average, what is the minimum average cost. So you take h of 109.454, right? Because it says find the level of minimize the cost. So then if I put that, right, what I'm going to do though is I'm just going to uh, I'm going to graph this. Sorry, I don't know why it does that. So I'm going to graph the cost function. So it's 0.002x, and then this is plus 24 divided by x. So this is a very strange function, as you can tell. Let's see what it says here. Special points. Yeah, do you see the minimum? So you see how this is a very strange function because it looks as though this function is always getting smaller and smaller, but actually it's not. Actually, my minimum occurs here. This is the minimum here. And the minimum here, if you see it, it says the x value is 109.545, right? And the y value is 0.438. So this would be 0.438, 0.438, dot, 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 which is approximately what? 44 cents. So if I were to sell between 109 and 110 units, the average cost would be minimized to 44 cents per unit. So then you would say, based upon this model, based upon the model for the average cost, selling a 109 or 110. So the reason why it's either or, because the number we get is not clean, right? It's a number in between 109 and 110. We can't sell 109 and a half units. So either sell 109 or 110 units. So if you're selling 109 or 110 units, the average cost will be minimized. So there's a little bit of estimation here, okay? Will be minimized to 44 cents.
So in this particular problem, when let's say we didn't have the calculator, we would plug in 10109.54 into the average cost function, not the total cost function they give in the beginning.
Because yeah, because we're actually sorry, this should be C prime. This should be
Yeah, that's what threw me off a little
oh
bit.
yeah,
I
yeah.
was
We're
okay.
doing a height. We're doing so much height that I was just thinking this height again. No, this is the average minimum average cost. So the average cost is around 44 cents per unit if we were to sell 109 or 110 units. And really, the answer to this question is this. It's not the 44 cents. It's the 109 and 110 units. Because they're asking us in the beginning, the question is find the level of production that minimizes the average cost. So the level of production is the number of units sold. And we figured that out from here. It's just that the graphing helps, guys. The graphing helps to understand weird functions such as this. So the average cost is enormous according to this graph if you sell very little. I mean, yeah, if you sell very little. But then it reaches a minimum for some reason when you sell this amount, around 110, 111 units. Anything less than that, or anything more than 110, or anything less than 109 will always be a bit more. So again, of course, there are limitations to these kind of functions because they model, right? They're models. They're not exact uh, functions.
Professor.
Yeah.
So I just have a question. Why did we for the minimum average cost? Why is it to the first derivative instead of just the average cost
Oh,
function?
sorry. Pardon me. Yes, you're right.
Oh, okay.
No,
Oh,
it should just be
the average cost function.
yeah, yeah, average cost.
Okay.
Because the derivative was used to find what would be that x value that makes my
Production level.
the derivative equal to zero.
Right.
So it doesn't make any sense. So if I plug it into my derivative, it would equal zero.
Right.
Plug it into my original function, which is the average cost function,
Okay. Okay.
average cost for that unit. So it would be 44 cents if I were to sell between 109 and 110 units. So yeah, thank you for that. We gotta make sure that's clear. So okay, so then let's maybe just recap really quick. So in the beginning, we learned about absolute min, absolute max, correct? And we only looked at it from the reference point of functions. That's it. There's nothing attached to the function. The function doesn't mean anything in real life. For the first few examples that we did, we only cared about the interval and we cared about the critical numbers. We look at the intervals, found the y values. We looked at the critical numbers, found the y values. The biggest is the absolute max, the smallest, absolute min. And then rinse and repeat, right? We just did the same thing again and again. Now taking a step up, and we're applying that same method, but now we're dealing with problems that are physical in nature or financial in nature, right? And the functions represent some kind of physical phenomena, such as a stone being thrown up in the air, or some financial phenomena as average costs, right? And you start to see that for these kind of problems, right, we're not so much concerned with the interval. It just so happens that for these kind of problems, it's kind of assumed in a way that the critical numbers that we get will either be a local max, not just a local max or a local min, it would be either an absolute max or an absolute min.
I feel like we use the interval, but like mentally,
Yeah,
as far as to find what's possible and what's not.
the interval, as you get to these kind of problems, the interval becomes less important. Whereas in the problems where we're dealing with just the functions and then they specify the interval, they become very important. It's a necessary thing. But when we talk about these kind of things, where it's like application to the real world, when we talk about throwing a stone in the air, we talk about cost functions, profit functions, right? The interval is not so specified, but for example, if you talk about the height of a stone, we know for a fact that the interval does begin with zero. We don't have negative values. So those are the small things that we have to keep in count of. For example, with average cost, right? The x values, they can't be negative either, because you can't be selling negative amounts of things. Because in the context of the problem, it makes no sense. So I should specify that my x values, right? My x value are is bigger than or equal to zero. In theory, you can sell an infinite number, right? But you see how we can't really say what's the limit of my endpoints here, because we don't know. We can sell 100 million, we can sell 100,000. Like it varies, correct? So the interval here doesn't become so, like, it's not so necessary to know, but it is good to know where to start from. Zero usually is the great starting point for all of these problems. Whereas in the other functions, right, in the regular, just general functions, often the interval is specified for us. So we're going to continue with this on Wednesday. We're going to be dealing with more, I would say, more complex scenarios where the function will not be given to us. The second level, I guess, to this is when we have to find the functions ourselves. So normally we're given functions, right? We're given that the cost function is this, or we're given that the height of the rocket is this. They give us our functions. Now on Wednesday we're going to talk about how we can find the functions for ourselves and then apply this whole first derivative test, second derivative test to figure out the maximum or minimum. Okay?